Cool. All right, so this first session will just be about point set topology. And the idea is that this class is about, the geometry class is going to be about manifolds, which are spaces that are locally, well, they're topological spaces, first of all, and they're locally, if you zoom in, they are locally Euclidean, meaning very close to points, you can find a map that makes it look like Euclidean space, meaning Rn. And this would maybe be some n-dimensional manifold. And by the way, maybe you don't know what all these words mean, but this is just an overview, so just take things lightly. But the idea is that to understand what's going on these manifolds and to be able to do calculus on these manifolds, which is basically the goal of this class, we have to understand both topological spaces that underlie these manifolds are topological spaces underlying. So we need to know what some basic topology, what a topology is basically, and stuff like that. And then on top of the topology, we put linear algebra structures and calculus stuff. So part 2 and part 3, which I already said in the email, but part 2 should be linear algebra. And part 3 will be reviewing multivariable calculus. And so this kind of grew out of this thing I noticed where, at least when I took multivariable calculus, I promptly forgot a lot of the things which turned out to be important in order to take this class, which is just what actually the derivative was, officially, what kind of object is it, and how do you formulate it in terms of abstract linear algebra, which is why I'm including those two. But certainly there's also people who have not had a point set topology class, and I was lucky to have one, but I think sometimes they're not in every university. So I wanted to at least get something where people could learn the basic definitions of topology, which include words like, so these are maybe the goals of this session. I just want you to be able to see the definitions of what a topology is. If you haven't seen that before, what open and closed sets are. Maybe get an idea for continuous functions and continuity, and these notions of compactness and connectedness. Okay, and maybe set you up to be able to look into more topology stuff when it comes up in the class. Okay, so yeah, that may maybe set you up to look up stuff later. Okay, so yeah, I guess I don't want to stall too long on the intro to this point, but so point set topology is about setting up what a topology is and what a space is. Okay, so topology has to do with turning things into spaces. Okay, so when I say a topological space, this is a notion that's defined in this area of point set topology, which maybe took like 100 years to develop all these very abstract definitions that go into all of these words. And it's very hard to maybe at first see why things are defined in such a way they are. You'll see everything is defined in terms of these open sets, including continuity, which you might remember what continuous means for functions on the real numbers, but in the abstract sense, it's kind of this weird notion of inverse images of open sets, right? And so, there's a couple strategies for trying to learn point set topology especially, but also this kind of applies to a lot of things in math, which is you can either go in very in depth, in detail, and try to learn all the things and like what each definition means and why it was defined in such a specific way. And that'll take you through like all the history of like, why did people look at defining a topology in such a way, and why did they define continuous functions to be this and not this other thing that also seems like it could be a good definition for continuous, right? And so you'll have to go through all that history. The other way of doing it is to just accept it and then move on, just be kind of uncomfortable with all the definitions, but like remember them. And then over time, as you start to use the concepts, the stuff will start to sink in and they'll feel more intuitive. And that's really, for the interest of time, for a lot of math, you kind of have to do that. So I'm going to encourage you to, if a thing seems like really weird, like why is it this way? You can certainly go in and look to some extent of like why is this defined in such a certain way? But a lot of the answers will come later when you start to use that concept and realize like how this thing is used, right? So like definitely compactness has a weird definition, but after doing a couple proofs that involve proving like compactness or using that something is compact, you start to get the feel for what compactness means. Okay. All right. So I talked maybe way too long about that, but let's just move on to some actual definitions. Okay. So I'm just going to kind of go through, again, the resource for this. I did send this out. But the resource I mainly used for this was Loring Tu's book on smooth manifolds. I think it's called Intro to Smooth Manifolds. Maybe introduction, maybe it's more formal than what I'm writing. And I'm just using the appendix. This is sometimes used as the textbook for the course, but not always. There's also a book by John Lee called Intro to Manifolds. Oh, maybe it's just called Introduction to Manifolds. So maybe it's technically no smooth, but he does mean smooth manifolds. There's a distinction, I guess. But I'm just using Appendix A, which is topology, meaning point set topology. Okay. And so mostly everything that I'm going to talk about today is in there. I based a lot of it off of there and pulling a little bit from some other places, but there's also a book dedicated to more topology stuff, which is James Muncre's. I think it's just called Topology, but this is a much bigger book. I would say, I think I already also wrote this in the email that I sent out, but I'm going to include it here. But let me just make sure which chapters it is. But yeah, so topology, I'm just maybe focusing on chapters 2 to 3, and then there's some more in chapters 4 and 5. Okay. 4 and 5. But this would take I spent maybe almost a semester using this book for a point set topology class. So that's, maybe I would use it if you want to look at one thing in particular in another perspective. If you're crunched for time, if you have the time, you can go in and read something like that. But yes, so these are some resources. And Loring Tu's book, as I said, is, I think, just a really good manifolds book if you are taking the geometry course. I highly recommend that book over John Lee, but that's just my opinion. So I know other people, even in the department, I've gotten into squabbles with that other people prefer John Lee's book, and I don't really prefer it, especially like on a first time reading. But okay, but so those are some resources you can look into. I think I sent Loring Tu's book right in the email. So, all right. So let's get into what topology is. Okay, so to begin, we have, let's picture Euclidean space, Rn, right? And whenever I write Rn, maybe we just want to picture R2, sometimes R3, but a lot of the stuff will be perfectly fine working in R2, and because we can just draw pictures like on here, this is R2, right? The tablet is displaying R2 right now. And we want to let's start with the definition. So define the open ball, the XR for X in Rn, and R some positive number to be the set. So this is hopefully starting from a more familiar place, right? But this is the set of all points in Rn such that the distance from X to Y is less than R. Right. And it's important that I put a less than sign and not a less than or equal to. And this is maybe the important part of it being open. Okay, so the fact that this is less than just tells me that it's open. If it was a less than or equal to sign, I would call it the closed ball. And maybe we'll get to something. Maybe we'll get to the closed ball in a little bit. Right, but if here's your point X, just to draw a simple picture, the closed ball is just, or sorry, the open ball is just the ball of radius R away. Hopefully this should be something people have seen before, but I don't want to assume that everyone's seen exactly this definition. Okay, and let's define an open set in Rn to be one such that, oops, well, I guess an open set U is one such that for every point in your open set, there exists a ball that sits inside your open set. Okay, and of course, the ball contains the point X. Right? Okay, so an open set is a set in Rn, and it can have some weird shape. And I'm drawing, maybe I'll use this dotted line thing here. Okay, it can be any weird shape. It can also have different pieces to it. But the point is that if I go to any point in particular, we call that X, I can draw a little ball around my point and still be inside of the open set U. Okay, or inside the set U. So U is maybe the union of these two pieces or something. And around each point, I can draw a little ball, and that ball might depend on each point. So if I go very close to this boundary over here, I can draw an open ball right here, right? And I'm drawing these dotted lines to mean that I'm not including the boundary for either of these sets. That was made clear, but okay. Okay, so this is how we usually define open sets in the context of Rn. Okay, so I'm including this thing for Rn, but I'm going to do it for more abstract topological spaces. But this is maybe the setup for it. Okay, and by the way, I'm going to export all these notes into a PDF. So if you're worried about having to like copy all this down, I'll send out this PDF after we're done here today. So if that makes things easier, hopefully that does. Okay, so yes, so an equivalent way of writing open sets is that so if I say a set U is open, I could say that there exists an open ball around each point inside the open set, or I could say that U is a union of some open balls, maybe X alpha or alpha, where alpha is some index in some index set. Okay. Okay, which just means that I can write the set as a union of open balls, and that union might be over infinitely many open balls, but I can write it as a union. Okay. By the way, if there are any questions, feel free to like speak out, throw anything in the chat if there's anything you want to ask. Okay. All right, so these are maybe two equivalent ways of saying what an open set is, right? You can say there is an open ball around each point, or it's a union of open balls like this. Right? Okay, so let's start with, maybe I'll, oops. Okay, so now we're actually starting with what a topology is. Okay, so this was all just set up for Rn. Okay, so topology in general is, oops. Okay, let X be a set to set up. And I'm going to define a topology on X is a collection of subsets. And I guess I will call the collection T for topology. And so T is some set of subsets. Okay, so each U alpha is a subset of X, where alpha maybe lies in some index set again. Okay, so there's just a bunch of sets, and we call each set U alpha an open set, right? So this is a collection of subsets that we call open sets. Call open sets. Okay. And so this is not enough. I need them to satisfy some properties. Okay, so I need the empty set and the entire set to be inside this collection of subsets. I need if, let me write this the way I wrote it here. So if U beta is a collection of sets in the topology for some beta in J. This is another index set. By the way, is it clear what I mean when I say index set? Does anyone have any question about that? It just means that I'm taking a collection of open sets here, right? So there's a bunch of U betas that are all in the topology. And I don't know how many there are. There could be infinitely many. There could be uncountably many. I don't want to just write like U1, U2, U3, all the way up to UN or something, because there could be more than finitely many, right? So the way to do that is to write it like this. Oops. To write it like I have done here, right? Okay. So if you have a collection of some of the sets inside the topology T, then the union of all these sets is also in the topology. Okay. So if we translate in the language of open sets, if you have a bunch of open sets in the topology T, or if you have a bunch of open sets on X, then the union of open sets is also an open set. Okay. Open sets is also open. Okay. And then I also need a property about intersections. So if I have U1, UN, so now I'm specifying that there's only finitely many, okay? And each UI is an element of the topology. So each UI is an open set in X. Then the intersection from I goes from 1 to n of UI is also in the topology, okay? So this says the finite intersection, or the intersection of finitely many open sets of open sets is also open. Okay. Okay, so this is a very abstract definition. I wanted to get it all down, but has anyone not seen this definition before? Maybe you can do the raise hand thing. Okay, so maybe have we all heard of these open sets and stuff. I don't know actually if anyone. Okay, cool. So that is a better starting off point at least. But yes, so you can go in and check that for these open sets in Rn that these satisfy all the properties. That's maybe just a sort of technical proof, but it's maybe worth doing just to verify that you know what the definition is. Right? But okay, so let me maybe go through some examples of topologies on spaces. Okay, I would say I guess it's not like there's some definitions where they're very technical and we don't use the definitions exactly as they're stated. And to some extent, a topology is a little bit like that. But we do sometimes use the fact that arbitrary unions of open sets are open and finite intersections of open sets are open. That does come in handy sometimes. So okay, so let's just go through some examples. Right? Okay, so I already talked about Rn with its unions of open balls, right? Okay, so that means the space here is X is Rn, and the topology is the collection of all sets which can be written as unions of open balls, right? Let's see. So that's maybe like one of the most classic examples. You can also say X is just any metric space. Meaning it has a metric function or like a distance function, which you might write as dx, y, right? Something like this. I guess maybe r greater than or equal to 0. Right? Have we seen metric spaces before? So metric spaces are maybe like the best example to think about when you think of topological spaces, but not every topological space is a metric space, but a lot of the ones that we work with are. And they're very good for just visualizing stuff. Okay, so yes. So any metric space and the topology on the metric space is, again, the set of unions of open balls. Where now open balls are just defined using this abstract metric rather than the concrete metric of Rn, which I think I also just wrote as the same way, right? I just wrote, yeah, I wrote it in the abstract way, but really in Rn, this was equal to x minus y, and you take the Euclidean distance, right? Or sorry, I guess it's just this. Where you think of these as like vectors and you're doing vector magnitude. Right. Okay. So yes, any metric space I think is a good visualization of topologies. There's also some weird examples with like finite sets. So let me see, I wrote some down. Some finite set examples. So I can kind of just like draw these. Let's say we have a set with 3 elements. And then I'm just going to specify what the topology is by drawing what the open sets are, right? So here's one example of a topology. Maybe I should like color it or something, but right. T is the sets in blue, right? So this is one open set, maybe call it U1, U2. And then, so we also always need to include the entire set X as well. And then we also need to include the empty set, which I can't draw. Right. And then you can check, is the union of any 2 open sets, if I take the union of this one, that's the entire set. So I'm still in the topology. And if I take the intersection of any 2, here there's nothing that intersects really other than just being a subset. So if I take the intersection of any 2 sets, I still get an open set, right? Okay, but you can draw like these other weird topologies, which again, I should make this blue. Okay, so maybe here's another example of a topology. Here's U1, U2, and then there's a U3 in here. And then, of course, there's always the entire set as one in open set as well. Right. So you can see if I included U1 and U2, I have to include U3 because it's the intersection of U1 and U2, and that's finitely many open sets. So if I just had 3 points, and I took these two as open sets, U1 and U2, this would not be a topology by itself, right? So this is not a topology yet. Okay, even including the entire set, this is not yet a topology because it fails to satisfy property 3, right? Property 3 that says that if I take finitely many open sets in the topology, then the intersection has to also be an open set, right? And here I have 2 open sets. If I take the intersection, I don't get one that I specified to be an open set in the topology. Does that make sense so far? Any questions about that? Cool. Okay, there's also these trivial ones, so let me just include trivial topologies. One is the indiscrete topology. Okay, and that's where you have any set X, and the topology is just the empty set and the entire set, and then you don't have any other sets in your topology. So there's no set that is called open unless it's the entire set or the empty set. Okay, and this basically in pictures, if you were to do it for the 3-element set, this is just, you just don't draw anything except for maybe the entire set as one open set. Okay. So this is a trivial topology because there's not these properties 2 and 3 of a topology, right? These arbitrary unions and finite intersections. These are true vacuously, right? Almost vacuously. Maybe you'll have to also check, I guess. Technically, there are some unions you can write down, but they're all kind of boring unions and intersections, right? Okay, the other trivial topology you can think about is the discrete topology. And this is a space X, and the topology is the power set of X, meaning every subset of X is in every possible subset. Right, so it's the set of all subsets of X. And this is on the far other end of the spectrum, right, where you call every single set open that you can, right? So I want to get across that you can have a set and there are multiple topologies on that set, right? And so a topology is a choice of one of these collections that you decide that these sets are going to be open and some sets are not going to be called open, okay? And it's, you know, if you start at one end of the extreme, you get the indiscrete topology. If you go all the way to the other end, you say every set is going to be open. Then you get the discrete topology. Somewhere in between is where there's some probably useful topology that you can use that describes what's going on. Okay. All right. Any questions so far? So I will take, I'm not going to speak for like an hour and a half straight, but I will take a break, maybe 2 breaks somewhere in there. But okay, so this is maybe what a topology is. Here's something, I went through some examples. Let's define, so we defined what an open set was, which is just, an open set is just an element of the topology T that you specify. I should also specify what a closed set is if I'm going to say what an open set is. So a set V is called closed. Okay, so the setup for this should be let X be a set with a topology T. Yeah, and a set with a topology T is sometimes called a topological space. Okay. Okay, so a set is called closed if the complement is open. X minus V is open. Right? Again, in other words, X minus V is a set inside of the topology that you specified. Okay. So there's this like common caveat whenever anyone defines closed sets is that just because a set is open doesn't mean it's not closed. These are not mutually exclusive concepts. So you can have a set that is both open and closed. For example, X, if xt is a topological space, meaning a set with a topology, then X itself is open, but then, and the empty set is also open, right? But this is the, X is the complement of the empty set, so X itself is closed. I don't know why I'm changing the way I'm writing stuff. So X is also closed, right? Because its complement is, maybe I should, it's really just because of this thing, right? So X is open. And because the empty set is open, X is also closed, right? So these aren't exclusive. But usually it doesn't happen that we get these closed and open sets, at least not of. What happens is you'll get something called a connected component. It's the full connected component of your set. So if you end up seeing a subset that is both open and closed, it's probably a full connected component. And if there's another open and closed set, that's like a different connected component that we'll see when we get to connectedness. Okay, so open and closed are not mutually exclusive, but I should give a better example here. So the closed ball in Rn, right, which I will denote like this, is the set of all points in Rn that are a distance less than or equal to r away. Right, and that is because if I draw this closed ball with closed boundary now, right, everything in here, the complement is everything outside, and it doesn't include the boundary here, right? So if I were to just draw the complement, it would be this everything outside of this open ball, and everywhere outside of the open ball, I can draw a little open ball around it, right? Which was our original definition of open, right? So you can say that this thing, or you can say this is a union of open balls, right? Where these balls have, I should be drawing dotted lines here, but right. So the point is you can prove this complement is an open set in Rn the way we originally defined it. All right. How's everyone doing so far? I'm kind of going for 40 minutes. So any questions? Doing okay? Thumbs up. Some. Okay. Cool. Okay, so let's talk about the subspace topology. Okay, so let S be a, oh, so now from now on, I'm going to assume X T is a topological space. So let X be a topological space. And let S be a subset of X. So if X has a topology, you know, S is just a subset. It doesn't necessarily have a topology a priori. So we can define a topology on it, induced from the topology on the ambient space X. Okay, so to define a topology on S, we have to specify what sets are going to be called open, right? So I'm going to say V is open or V is called open if, and this is a definition of what it means to be open inside of S. So V, a subset of S, is called open if V is equal to S intersect U for some open set U inside of X. Okay. Right, so let me draw just a picture of what's going on here. Let's say I have some set S that looks like this, and this is inside the space X. Then if I have some open set U like this, and I take the intersection right here, this is exactly the open sets of S, right? These intersections of open sets with the subset. Okay. So if you look at what's going on with like the boundary, if this was R2, right? Your set S could be maybe some closed off bound, like set with some boundary to it. And so V would be kind of this half closed, half open sort of deal, right? But because we can draw it as the intersection of some open set with this maybe half closed set S, in this case, this is still open in the set S, right? So V is open, I should specify, V is open in S for some open in X set U. Okay. So this is called the subspace topology in S. So. Okay. And so this is, I'm just defining it as a topology, but you have to maybe prove that it satisfies the axioms of a topology, which is if you took a bunch of open sets and took their union, is it still open? And because everything's relating back to open sets in the ambient space X, all these axioms will go through. Just you kind of have to just take the intersection with the S a bunch of times. Okay. Okay. Yeah, I think that's all I wanted to say about subspace topology. There's not really too much. Next, I want to talk about bases for topology. Okay. So let X, T, okay, yeah, I guess I'm writing it again. Be a topological space. Okay. And I'm going to define a basis for T, oops, basis, to be a collection which I will call fancy B. And it should be a collection of open sets. So it should be a sub-collection of the topology T, such that for every open set U inside of X, and every point inside of U, there exists a set B inside of this smaller subcollection, script B, such that X is inside B and B is inside of U. Okay. So the idea is, again, just drawing it out, this will be maybe a familiar picture from just earlier. So this is the set X, and then maybe I have some open set U. Just imagine that I've done, open boundary here. And then I have some point inside of U. What a basis says is that you can draw a little set around your point and be entirely contained inside of U. Okay, and you can do this for every point. So this is analogous to the collection of open balls in the Rn case, right? So the topology in Rn, we had the topology, which was a set of all unions of open balls. Right. But then we just had, maybe you can specify a collection of just the open balls, right? I'll write it like this, open balls. Right. But of course, open sets can have weird shapes. They can look like kind of crazy. But open balls are specifically just like this specific form, right? But what this says, it's enough to specify what these open balls are to generate the entire topology. Okay, and so there's a fact that kind of follows through, which is that the basis, so I guess let B be a basis for T. Then we have that B generates the topology T in the following sense. Right. So completely analogously to how in Rn, we had this property about open balls, that around each point inside any open set, you could draw an open ball around it, right? And then I said that every open set was the union of open balls, right? So this works abstractly too. So this is in the general case for X, T. B generates T in the sense that for every open set U inside of X, U can be written as the union of sets in B. So maybe I'll put some index here. Inside of this collection, okay? Okay, so it's enough to use these basis sets to generate the entire topology. Okay.
Excuse me.
Yeah.
So I had a doubt. So if I recall correctly, the definition I read for base of a topology had another condition. So the condition was that if you have if you have two elements from the basis, and if you choose an element in the intersection of these basis elements, then there must be a basis element which contains that element and is contained in the intersection.
Yeah, that's an equivalent.
Does that?
Yeah. So a basis you can write equivalently as a collection be like this, such that I think it's like X is the union of all over all the sets B inside of this basis. That's one, and then two is this intersection property that you're talking about for every B1 and B2 inside of this collection. B1 intersect B2. There is another basis element or something like this, right? So there exists a B3 inside of the basis such that, sorry, I'm mixing this up a little bit, but such that, oh, I guess, yeah, okay. So for every point,
we have to choose a point
inside of the intersection, there exists a B3 such that, let me order this correctly. So I'm not going crazy, okay. So this is an equivalent definition, okay. So this says that if you have a collection of sets that satisfies this property, then it generates a topology on X. I guess okay, so it's a little bit, it's only slightly different in the fact that you can specify a basis without saying that it has anything to do with any topology starting on your set. And then you can say that this generates a topology on your set X. But this is, if you have a topology already, then a basis for that topology, it's enough to satisfy this thing. Okay, and then if you look at the topology that this generates, this B will be a basis for that topology, and etc. And if you look at the collection of open sets that satisfies this basis property, it will be a basis in the sense of this second description. Okay, but yeah, that's also a thing that you can look into further. But I really just wanted to draw the connection with open balls, and sometimes with working with a topology, you don't want to work with every possible open set if you're trying to prove something about a topology, because the amount of open sets can be kind of crazy. But it's enough to just say something about all the open balls, and then you've proven something usually for the entire topology, because the open balls generate the whole topology. Right? But that was the idea I was going to use. But yeah. Yeah, any other questions? Okay, so I think I'm gonna just define one more thing and then take a break. And then we can continue a little bit further after that, but let's see. I think I want to skip a few things, but so there's a few things that I definitely couldn't do everything that I wanted to do because there's not so much time, but I will list things that you can look into further, and knowing the definitions, if you haven't seen them before, or at least got a refresher on them today, it should be easier to look into them. And I think Loring 2's appendix is really nice to read if you just want to get a refresher on some of the topology stuff in there. But okay, but I'll talk about what I skipped over a little later. So what number was I on? This was bases. This was number 3, so I'm going to do number 4. Continuity. Okay. Okay, so I think for Rn, let's review what continuous means for a function from Rm to Rn. Okay, so I guess Rm to Rn. I guess I might ask someone here, does anyone remember what it means for a function to be continuous for Euclidean space? Or any metric spaces? I think you can do it for metric spaces, if you, right? Yeah. It's one of these classic definitions. If anyone wants to, if anyone feels brave enough to, yeah.
Yeah. So so if we have some epsilon greater than 0, and there is some small positive number delta, such that if we choose like 2 points, fx and fy close enough in the range, so that if like fx and fy are less, the distance between fx and fy is less than epsilon. Like for every distance between fx and fy should be less than like is less than epsilon, given the fact that we are inside this ball of radius delta.
Yeah.
Yeah, I think like what you were doing was fine, because you were like if.
Yeah. So for all x, y, distance between them is less than delta, right? Yeah. Yeah, so it's this epsilon delta definition, right? Which is like infamous as like, oh, you're working with epsilon and deltas in analysis or something, right? Yes, so this is continuous, right? And so all these things about epsilon and deltas, right? We want to, in the abstract case, reformulate to be working with open sets, and maybe open balls is nice to work with, right? So I'm going to translate these into wherever I have a statement about distance being less than epsilon. I want to turn it into something like I could say this statement is the same as f of y being in the set be f of x with an epsilon radius, right? This is like the same thing, right? And similarly here, I could say this is the same as y being in the ball of radius delta around x, right? So I'm going to define, first I'm going to define a continuous at a point, which sometimes is used. Then I'll define just continuous in general. And then we'll take a break after defining continuous continuity. Okay, but here's the idea. Okay, so let now x and y be topological spaces. And I'm not specifying what exactly the topology is, but maybe you call them T and S if you wanted, but I'm just going to say X and Y have some topology, so they have sets on both of them. They have some subsets that you call open, right? So you made some choice to distinguish some open sets over others. So let X and Y be topological spaces, and let F be a function from X to Y. Then F is called continuous at a point X inside of big X if for every open set, let's see, for every open set V inside of Y, such that f of x is inside of V, there exists an open set U inside of X such that U is inside of F inverse of V. Oh, and X is contained inside this one. Okay. All right, so this is one definition. I can draw the picture. It might help a little bit, just where these sets are, because I just defined these out of nowhere. But here's maybe the point X, and here is the point f of X. And then let's say we draw some open set V, and I'm not going to bother doing boundaries because it might just get messy. So just imagine this is an open set V, right? And then if we pull this back by F inverse, the inverse map, right? Right, just F inverse maps the entire set V into some big piece. Maybe there's also some other pieces, right? So maybe it's a lot of different pieces. Like maybe both of these sets both get mapped into this one region, right? So that's okay. That could happen. All of that I'm saying is that there is some open set U around X that fits inside of F inverse of V. Okay. But actually, so this is one way of defining continuous, but you can like very easily reformulate stuff once you start getting more comfortable with open sets. So it could say equivalently, for every V inside of Y, such that F of X is in V, open. There, no, sorry, you don't have to say this. F inverse of V is open. Wait, sorry, no, this is continuous at a point. Okay. Sorry, I think I have this a little bit wrong. I'm jumping ahead of myself a little bit, but sorry, ignore what I just said there. But the point is that these open sets here are supposed to play the role of these epsilon balls and delta balls in the Rn case or in the metric case, right? So let me just write down the idea, which is you treat open sets around points like very small neighborhoods, right? So around that point, right? So if I say, let U be an open set containing X, right? The idea that I want to have in my head is that U is some very small neighborhood, and usually I can picture open balls because they are enough to generate the whole topology. But I want to picture that it's very close to X and just kind of getting just like the surrounding points around X, right? So that's the idea, is that open sets are supposed to describe what's happening. If you take small enough open sets, you kind of are looking at what's happening just very close to a nearby point X, right? And you can see how this is helpful for when you start talking about stuff in calculus, right? But in calculus, you need to be more quantitative about it, which is why you do want these open epsilon balls and delta balls, right? But topology kind of distills all this and makes it like, what is the essence of being around a point, and what is the neighborhood of a point really, right? So this terminology neighborhood is also used a lot, right? So neighborhood is some notation. A neighborhood of X is another word for just an open set containing X. Okay, so you might see this a lot, and it's trying to capture this idea of you're trying to zoom into a point and seeing what's happening locally. Okay, and so again, going back to this definition of continuous, as I said with like the definition of a topology, it can be kind of removed from what these epsilon balls and delta balls are, but I'm trying to at least get a little bit of the point across of like these U's and V's are playing the role of B, B delta and B epsilon. Okay. Okay, so that's the idea. Let me just now define continuity in the more general case, which is just continuous everywhere. So let f be a function between topological spaces. Okay, and f is called just continuous if for every open set V inside of Y, f inverse of V is open inside of X. Okay. And it's a little bit of an exercise to go through and translate this thing with open and using the fact that the open balls in Rn generate the topology, you can go in and translate back to the epsilon delta definition. And that's a good, I think, exercise to do. So I'll just leave it at that. Okay. All right, so let's maybe take a break. I'm gonna pause it, or I guess stop the recording.